Okay, so the next thing we will look at is the relations between edges and vertices in a graph. We want to have some definitions and some concepts that will help us understand the structure of a graph. So the first notion is that of adjacency. So if you have two vertices in a graph, say x and y, and maybe you have other stuff in the graph, but these vertices x and y are called adjacent if they are joined by an edge. So if these are houses in a city, if there's a direct road from x to y, then these houses are adjacent. And as we saw with the pentagon example earlier, it doesn't really matter how you draw the graph if they are physically close to each other in your drawing. The only thing that matters is that there is an edge. Notice that joined by an edge means joined by at least an edge. So you can have as many edges as you want. As long as there is one edge, you're fine. And two edges are called adjacent if they share a vertex. So if you have an edge, say E, and another edge F, then since they have a vertex in common, they are called adjacent. Now comes the first numeric concept, that is the degree of a vertex. So the degree of a vertex is the number of edges that are incident to the vertex, meaning that connect to this vertex. So let's look at an example. Let's look at the following graph. Right. So what are the degrees of these vertices? You can pause the video and work this out for yourself. So this vertex has degree 0 because no edges are incident to it. This has degree 1 because there is one edge. This has 1, 2, 3 edges. This one has 2. This one also has 2. Doesn't matter that they go to the same other vertex, it's just you have 2 edges. This also has degree 2. This one has degree 4. You might protest and say that, okay, we see 1, 2 here, and the loop surely is just one extra edge. But a loop is counted as 2 because, philosophically speaking, it goes in and out. And also, if you want to remember this, zoom in on the vertex, and you will see that there are, in fact, 4 branches going out of the vertex. So that is the degree of a vertex. And you can get a lot of information about the graph by just recording these degrees, and that gives you the degree sequence. So it's just all the degrees written in increasing order. So here we have the degrees in increasing order, 0, 1, 2, 2, 2, 3, and 4. So for this graph, you get the degree sequence 0, 1, 2, 2, 2, 3, 4. And now there are some interesting facts about these degrees and degree sequences. So the first theorem is called the handshaking-lemma. And the handshaking-lemma says that in any graph, the sum of the degrees is an even number. So what is the proof? The proof is quite short. So the sum of degrees is twice the number of edges, because if you have an edge, then the edge will have 2 endpoints, so it will contribute by 2. So if I have my 2 vertices here, x and y, if I have an edge between them, the edge will add 1 to the degree of x and 1 to the degree of y. Similar, if I have a loop, the loop will add 1 to the degree of x and then again 1 to the degree of x. It adds 2 to the degree of x, and therefore the sum of degrees is the 2 times the number of edges, which is an even number. So in this case, x has degree 3, y has degree 1, and the sum 3 plus 1 is 4, which is an even number. Why is this called the handshaking lemma? Well, now we are in quarantine times, we're not allowed to shake hands, but in a world where you can shake hands, when you shake the hand of a person, each handshake involves 2 hands. So that's why it's called the handshaking lemma. As a consequence of this, the number of odd degree vertices is even. So in a graph, you will have a bunch of vertices. Some have degree even number, some have a degree being an odd number. And the number of those vertices that have an odd degree is even. Why is that? It's because the sum of degrees, which we agreed by the handshaking lemma is an even number, is the sum of all the odd degrees plus the sum of all even degrees. The sum of even numbers is always even, so the sum of all odd degrees must be even. Now, if you have a bunch of odd numbers, the only way that their sum is even is that you have an even number of odd numbers, proving the corollary.